Okay, so this is part 2 of the chemistry mid-year exam review, and we're going to pick up here with electron configurations. The electron configuration for magnesium, and it asks for the full configuration. So, you have to remember the progression of the orbitals, which goes like this: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and then it would go to 5s and 4d if we needed to go that far. We're not going to need to go that far for any of these, but that's the order that they go in. And then you have to know that every s orbital, whether it's a 1s or a 5s, can hold up to 2 electrons. Every p can hold up to 6. D can hold up to 10, and then F could hold up to 14. So, for magnesium, which is element number 12, we're going to always start with 1s. I can put 2 in there. 2s, I can put 2 in that because it's an s. And then I get a p on the second level, which I can put 6 in. And then 3s, I can have 2. So if I add up the electrons, there's 1s2, 2s2, 2p6, 3s2. 2 plus 2 plus 6 plus 2 equals 12. So that's how many electrons I needed, that's how many I have, and I followed the order that we did down at the bottom here. The full electron configuration for the nitride ion. Okay, so the fact that it's an ion has a charge of -3, which means it has 3 more electrons than normal. So nitrogen is normally number 7, but I have to add those 3 electrons, so I'm going to write a configuration that has 10 electrons in it. And I start again, because it's the full configuration, always start a full configuration with 1s2, then 2s2, that gives me 4 electrons, 2 and 2. The next thing in the list is 2p, and that can have up to 6. 2 plus 2 plus 6 gives me 10, which is how many electrons I said I needed for nitrogen, plus 3 more electrons, which gives it a -3 charge. So 1s2, 2s2, 2p6. The next one asks for an abbreviated configuration for copper. In the abbreviated configuration, you start with a noble gas, and what you do is you take the element that you're starting with, copper, look it up on the periodic table, go up 1 row above your element and go all the way to the right. And the element that you'd find in this case is argon. That's a noble gas. So you put the symbol for argon in brackets, and then you're going to start the configuration after that with the row number of your element, which is copper, is in the 4th row. And the rows all start with S. So it goes 4S, 2. And then the next thing on our list down at the bottom here is 3D. 3D can hold up to 10, but argon was 18. That's element number 18. So that covers the first 18 electrons. Then I have the 2 more in the 4S. That's 20. Copper is element number 29, so I only need 9 more electrons there, even though I could have 10. So that's the 29 electrons that a neutral copper atom would have. Okay, what group are these elements in? And in this case, what it's asking is some of the groups on the periodic table, the columns that go up and down, have special names. And each of these elements comes from one of those groups, so you need to know what the group names are for these particular special groups. Fluorine, F, is in group number 17, which is the next to last group on the right, and that group has the special name of halogens. So that's chlorine, fluorine, iodine, bromine, astatine. Those are called halogens. Strontium is in group number 2, which is the almost first one on the right, so the second one in. Those elements are called alkaline. All the elements in that column are called alkaline earth metals. Okay, so it's a reactive metal in group number 2. Xenon is in the very last column on the right, number 18. All of the elements in that column are called the noble gases. So starting with helium at the top, going on down, neon, argon, krypton, and so on, those are all called the noble gases. And then potassium is in group number 1, the first column of the periodic table. All those elements that have the 1 valence electron, they are called the alkali metals. So make sure you know the names of these special groups. Have an idea of which elements on the periodic table are metals or nonmetals or metalloids. Remember, the ones on the left are metal. The ones on the right, sort of upper right-hand corner, are the nonmetals. And then that zigzag line that separates metals from nonmetals is called the metalloids. Which atom in each of these questions, 38 and 39, has a larger atomic radius? So atomic radius and ionic radius would have basically the same trend. And the trends here are that as you go from left to right, the radius gets smaller. As you go from top to bottom, the radius gets bigger. Okay, so when you're looking at pairs of elements like carbon and silicon, you have to look at, well, which one are they left and right or up and down? Carbon and silicon are in the same group. Silicon is one row below carbon. So in this case, we're looking at the up and down relationship. As you go down, they get bigger. So silicon would have the bigger radius, and that's because it has more electron shells, more energy levels, which makes it bigger. And then we're looking at iron and copper. They're in the same row going across. So now we're looking at this relationship. Left to right, they get smaller. Well, iron is farther left, so it's the bigger of the two. And that's because there are more protons, fewer protons in iron pulling on the electrons. Fewer protons pulling on the electrons, and that makes it bigger than the copper, which has more protons in its nucleus pulling on the electrons, so they can pull those electrons tighter, makes the radius smaller. And then the next group, which has the higher ionization energy? Well, ionization energy has the exact opposite trend. As you go left to right, it gets bigger, and as you go top to bottom, it gets smaller or lower. So oxygen and selenium are in the same column going up and down. Selenium happens to be below oxygen, which means the higher one on the table, farther up, is going to have the higher energy. For the same reasons as the radius changes. Okay, fewer electron shells means the electrons are closer to the nucleus, and that means the oxygen holds those electrons much more tightly than the selenium. The selenium's electrons are farther away from the nucleus, so it can't hold them as tightly. And then we've got potassium and calcium, which are in the same row. Calcium is farther to the right. And in this case, the one that's farther to the right has the higher ionization energy. Again, the same reason. More protons means stronger hold on the electrons. Okay, so the trends are ionic or atomic radius go down from left to right and go up from top to bottom. Ionization energy, or if I can fit it in here, electronegativity. Electronegativity follow this same pattern. Goes up from left to right and goes down as you go down the periodic table. So the biggest atomic radius is the one on the bottom left. the biggest electronegativity and ionization energy is the ones on the top right. So they kind of go in opposite directions. What are the formulas of these compounds? Well, sodium oxide, and what you have to remember here is what are the charges? Sodium has a charge of +1. Oxide has a charge of -2. So if I write the symbols for the elements and then switch the numbers around, Na2O, this is O1, we just don't write the 1. Aluminum sulfide. Well, aluminum has a charge of +3. Sulfur, which is sulfide, has a charge of -2. Again, swap the numbers and you get Al2S3. Calcium oxide. Calcium is +2. Oxygen is, -2. So if you switch those around, they actually get 2 and 2, but you can simplify that to 1 and 1. So just be CaO, one of each. Iron 2 chloride. The 2, the Roman numeral 2, means that iron has a +2 charge. Chlorine always has a -1 charge. So I've got to switch those numbers around. Iron chloride 2, FeCl2. And then we get beryllium fluoride. Beryllium has a charge of +2. Fluoride has a charge of -1. Switch the numbers and I get BeF2. Okay, so write the name for these compounds. Now some of these are ionic, some of them are covalent. The way you can tell is that if it starts with a metal or if it starts with a polyatomic ion, it's ionic. So, and in that case, you don't have to do too much other than write the name of the first element, sodium, and then you write the name of the second element, sulfur, but you have to change the ending to sulfide. Now in this problem, we've got two nonmetals, phosphorus and oxygen. So it's not an ionic compound, which means I need to include a prefix to tell me what the number is that goes with each element. So this is tri-phosphorus, tri meaning 3, and then 8 is octoxide, octo. But I'm not going to put two O's in the middle, so we call it octoxide. 49 has the metal tin, it's SN. And sulfate is SO4. There are two of them. That has a charge of -2. Tin is an element that can have more than one charge, so I need to say that in this case, since there's two sulfates with a -2 charge each, that's a total of 4, which means my positive charge has to be 4. So I put a Roman numeral 4 next to the tin, and then sulfate. And two nonmetals, nitrogen and fluorine. So it's not ionic, which means I need the prefixes, so this would be called dinitrogen. And there are 7 fluorides, so that's heptafluoride. Dinitrogen heptafluoride. Okay, Vesper theory and shapes. So first you're going to have to draw the Lewis structures for each of these. And so to do that, you're going to go through the NaSl. Okay, and for A, you're going to end up with this Lewis structure. Hydrogen bond, hydrogen bonded to carbon with one bond, a triple bond to nitrogen, and then they're going to be a lone pair on the nitrogen. This shape is going to be linear, and you'd figure that out because there are 2 bond regions on this central atom of carbon. There are no lone pairs on the carbon. Anytime you have 2 bond regions, whether it's a single bond or a triple bond, those are each separate bond regions. So there's 2 bond regions, no lone pairs. That shape is called linear. It's a straight line. For B, you're going to end up with a diagram that looks like this. PBr3. Each of the bromines is going to have 6 lone pair electrons. The phosphorus is also going to have a lone pair on the top here. 3 bond regions. Always for the shape, we're only looking at the center atom. So there's 3 bonds and a lone pair. And if you look that up on your chart, that is called a trigonal pyramidal shape. Pyramidal. C, this is one of the exceptions to the octet rule because boron doesn't need 8 electrons. It can get away with 6. So we've got 3 fluorines, each with 3 lone pairs bonded to a boron, which has no lone pairs. So 3 bond regions with no lone pairs is called trigonal planar. And the last one, carbon tetrachloride, CCl4. Each chlorine is going to have 6 lone pair electrons in a bond. The carbon ends up with 4 bonds and no lone pairs. And if you look up a central atom with 4 bond regions and no lone pairs, it is called tetrahedral. All right, what is the polarity of these molecules? So NH3 looks like this. And the bonds in the molecule, you've got nitrogen connected to a hydrogen. That's always going to be a polar bond. And since it's got a lone pair at the top also, that means this area is going to be negative, and then the hydrogens are all going to be a little positive. So this has polar bonds and polar molecule. Okay, so they're all polar. B, which is the BF3, we already saw in the last problem as well. The fluorines are going to draw the electrons away from the boron. So these bonds are all polar. And you'd look that up by looking at the electronegativities of the two. But in general, if you've got fluorine, nitrogen, or oxygen connected to anything except sort of each other, it's going to be polar bonds. Now the molecule in this case, because you have fluorine at all 3 corners of the triangle, even though each one of them is a little bit negative, there's no positive side to this molecule. It's 3 negative corners, and the positive is in the middle. So when the positive is stuck in the middle with the same charge all around it, or could be the other way around, the negative in the middle with the positive all around it, it is a non-polar molecule. When it's the same on all sides, it's non-polar, even if the bonds are polar, which they are. And then we've got C, which is Br2. There's 2 bromine atoms bonded together. Since you have the same thing on both ends of this bond, the electronegativities are the same, so these are non-polar bonds. And again, since it's the exact same thing on both sides, it is a non-polar molecule. And finally, we've got HCN. Oops, that's a triple bond, not a quadruple bond. And the lone pair over here. The electrons are being pulled from the carbon, from the hydrogen toward the carbon, but then they're also being pulled from the carbon toward the nitrogen, which makes this end of this molecule really negative, It makes this end of the molecule really positive. The bonds are polar, and the molecule is polar because it's got a negative end and a positive end. So there you have it. Those are the types of questions that will be on the final. They're all multiple choice on the final, so there won't be as much, necessarily as much work. You might have to do some of this work to answer the questions. Come see me if you're still unsure about a lot of this stuff or any of this stuff. We can go over individual problems as needed, and we'll see you soon.